So now we turn to the subject of molecular electronics. As a physicist, I have always been amazed at the speed with which my chemist colleagues solve the multi-electron Schrödinger equation in their head, until I discovered their secret, which is Lewis structures, a wonderful guide to chemical bonding, and we'll introduce that first, and that will help us understand how molecules are built up. We will then talk about the various approaches to calculating molecular orbitals for complex molecules, and deal with molecular orbital theory, the Huckel model, and hybridization of atomic orbitals. And we will discuss how delocalization of electrons in organic ring systems decreases the energy of the electronic states. This theory is all very well and good, but it's very hard to do precisely. And so the most useful tool available to the chemist is electrochemistry, which allows one to order electron donors and electron acceptors quantitatively, one with respect to the other. Of course, no calculation involved, it's a measurement. So this is an extremely important tool in molecular electronics. We'll then talk about electron transfer reactions between molecules. The Marcus theory is simply an extension of Kramer's theory, but specifically to encompass electron transfer, and it's another example of an emergent phenomenon in a nanosystem. And then we will talk about charge transport in molecular solids, in particular hopping conductance, and then end with talking about what everybody thinks of when one mentions molecular electronics, which is single molecule electronics. Can we make something like a single molecule transistor? This idea of single molecule devices comes from a classic paper by Averum and Ratner, in which they proposed constructing a diode, a single molecule diode. So the idea here is to have one electrode, which I'm showing here, energies plotted this way. So here is the Fermi energy, and we've applied a bias to a second electrode, moving its Fermi energy down like this. Now, if the gap between the electrodes is so big that the direct tunneling rate is 0, then the only way for an electron to get from here to here is via intermediate states on a molecule. And what Ratner and Averum proposed was that on one side of the gap, one have this molecule TTF, and on the other side of the gap, this molecule TCNQ. So the occupied electronic states of these two or available electronic states are separated in energy by about an electron volt. So here's TTF, and here is TCNQ. The result is that an electron can only pass from this electrode to this electrode via these states in this direction, because the Boltzmann factor for going the opposite way, uphill against this energy barrier, is tiny. You can see it's on the order of e to the power 40, or minus 40. The molecule below is an example of a practical single molecule electronic device. We talked about this when we discussed chemical synthesis in chapter 6. It's this light to charge converter. So specifically, this chromophore in here acts to convert a light wave into an electron in an excited state, which jumps onto this buckyball, and a hole in the ground state, which is filled from this keratin molecule very rapidly. So a plus charge sits on this molecule and a minus charge on this molecule, and they're available to do useful chemical work. We'll address many questions that arise in the whole idea of molecular electronics. Specifically, what are the electronic states occupied by electrons on complex many-atom molecules? We know the electrons are localized on them. What are they? How do molecules gain and lose charge to form ions? What makes a donor? What makes an acceptor? How do charges move through a solid molecular material in which they're intrinsically localized on the molecules that make up the material? We'll address the question of, can a linear, one-dimensional molecule make a wire? Is there such a thing as a molecular wire? And then finally, we will talk about how electrons are transferred between metal electrodes and the effect of molecules in the tunnel gap between metal electrodes, how the Fermi levels of the metal align with orbitals available on the molecules, and the transition from tunneling conductance to hopping conductance.